In this video, we're going to talk about how to solve separable differentiable equations. And by the word separable, I mean you can separate the x and the y in the equation. This corresponds with section 11.4 in your textbook, separation of variables. So if we look at the first given differential equation, we have dy over dx equals negative x over y. So the first step you want to do is separate the x and the y to different sides of the equation. And we're also going to consider the dy over dx as a fraction that we can also separate. So for this first equation, I want to move the y to the out of the denominator. So I'm going to multiply both sides by y. So I get y dy dx equals negative x. Then the next step I want to do is I want the y dy to be together on one side of the equation. And then I want the x and the dx to be together on the other side of the equation. So since dx is in the denominator, again, I'm going to multiply both sides by dx. So I get y dy equals negative x dx. And then the idea is that we want to integrate both sides. So we're going to put an integral sign in front of both of these. Because in order to solve a differential equation, you're looking for the antiderivative. Integral symbol means find the antiderivative. So the antiderivative of y will be y squared over 2. The antiderivative of negative x will be negative x squared over 2. And then we're going to put a plus c on the x side. This is an indefinite integral. There are no endpoints. There's no given point to solve for c, so we just leave c in the equation. And then the last step is to solve for y. So I'm going to multiply everything by 2 to clear out the over 2's. So I get y squared equals negative x squared. And now c represents any number. So if I take 2 and I multiply it by any number, I get back any number. So I'm not going to put plus 2c. I'm just going to put plus c. And then the last step to get y by itself is to square root. So I'm going to use a plus or a minus because I'm square rooting. Negative x squared plus c. So again, the idea is to get one variable with its matching d whatever on one side of the equation and the other variable with its matching d on the other side of the equation. And if you notice, we got a few steps right here. Get all the x's on the right, all the y's on the left. It doesn't necessarily have to be the right and the left. Integrate both sides, solve for y, and solve for c if possible. In example 1 and 2, we're not going to be able to do step 4, but we'll get into how to solve for c in a few more examples. So in example 2, we're solving for dy over dx equals ky. So notice there is not a k in either the top or the bottom of the derivative. So that must mean that k is a constant. It is not a variable. And that's important. We're just going to treat k like a number. So we want to still, the y needs to be on the side with the dy. So I'm going to divide the y or multiply by 1 over y to move it to the other side. So I get 1 over y dy dx equals k. And then again, I need to get the dx out of the denominator, so multiply both sides by dx. So I have 1 over y dy equals k dx. And then you're going to put an integral sign in front of both of these because we're finding the antiderivatives. Integral sign means find the antiderivative. So on this side, the antiderivative of 1 over y is actually ln absolute value y. Now, k is, again, a constant. It's a number. The antiderivative of 2 would be 2x because there's an x here. So the antiderivative of k is kx. And then we're going to add the plus c. We always add the plus c to the x side, never to the y side. And now we want to solve for y. So in order to cancel out the ln, we're going to have to raise both sides as the exponent of an e. So e to the ln y is just y. And we still need those absolute value bars. Maybe we'll be able to drop them, maybe not. On this side, we have e to the kx plus c. Now, if you think back to your exponential rules, e to the x plus y was the same thing as e to the x times e to the y. Hopefully that's familiar. So we're going to break this up. And now I can actually drop the absolute value bars because an exponential function is positive. It's above the x-axis by its range. So it's already positive, so I don't need to keep the absolute value bars. So I'm going to write this as e to the kx times e to the c. The reason we do that is e to the c is actually just a constant. It's just a number. It's like e squared. E squared is a number that you could find in your calculator. So people will replace this e to the c with just a c. So really we have c e to the kx. And some people change the letter. You may see this written as a e to the kx, or again, it could be any letter. The letter doesn't matter. It just represents a constant. And since y is by itself, this is the antiderivative function. Now, in example 3, notice we're given a derivative, a differential equation, but we're also given a point. And this is where we're going to be able to do that step 4 on the steps list. We're going to be able to solve for c. So we're going to start it out the same exact way. Now, notice that there's y's in both of these. Now, I cannot add and subtract things to opposite sides because I want it to be multiplied by dy dt so that I can then multiply by dt on both sides to move the variable over. So what I have to do first is GCF. So I'm going to factor that y out. I'm going to leave everything else. So if you have a variable in multiple terms, you always need to start by GCF. And now I can divide the y to the other side. Oh, I forgot to bring down my dy dx, or dy dt. Okay, so, and then the next step is to move that dt to the other side. So I'm going to put parentheses around this because it's dt times all of that, 2 minus 2t. So I have 1 over y dy equals 2 minus 2t dt. And then I add my integral symbols to tell me to find the antiderivative. So 1 over y becomes ln absolute value y. Antiderivative of 2 is 2t in this case because the variable is t, not x. Make the variables match. And negative 2t becomes negative t squared plus c. And so again, I'm going to take the e of both sides so that I can cancel out the ln. Anytime there's an e and an ln next to each other, they cancel out. And I'm going to write this as e to the 2t minus t squared times e to the c. So I really just have y equals c e to the 2t minus t squared. Okay, so that's got us to step 3. We've solved for y. But now that we have a point, we've got to go farther, and we've actually got to solve for c. So we're going to use this point. So 0 is a t value, and 5 is a y value. So I'm going to plug in 5 for y, and 0 for t. So I get 5 equals c e to the 0. Hopefully you remember that anything to the 0 is 1. So e to the 0 is just 1. So c must be 5. So then we write our final answer with 5 in the equation instead of c. In example 4, they've changed the variable on us again. We have a p instead of a y, but we're going to treat p just like it's y. So again, it's important to note that you cannot move variables to the other side by addition or subtraction. I cannot subtract this p because then I would get dp dt minus p equals 4, and that's not useful because the goal is to get the dt on the other side. And if I try to multiply both sides by dt, what am I going to end up with? I'm going to end up with dp, oops, sorry, that's a minus, minus p dt equals 4 dt. And that really makes no sense. We cannot take the antiderivative of this. So we don't want to do it this way. What we do want to do is think about this p plus 4 as one whole unit. So we want to take dp dt, and we're going to actually divide or multiply by 1 over p plus 4. So on this side, we just have a 1. So now we have 1 over p plus 4 times dp dt, and we can multiply both sides by dt. And this way, the dt's just cancel out on the left. So we have 1 over p plus 4 dp dt equals 1 times dt. So this is what we're going to be integrating. So the antiderivative of 1 over p plus 4 is very similar to the antiderivative of 1 over x. The antiderivative is just going to be ln of p plus 4. Antiderivative of x is just going to be t, and then we add our plus c. So I got to take the e of both sides. So I have p plus 4 equals e to the t plus c. So again, I can separate this as e to the t times e to the c, and so we just write it c e to the t. Notice, again, I dropped the absolute value bars because e to the t is positive. So I don't need absolute value bars because it's already positive. And then I'm just going to subtract the 4 to get the p by itself. P is like y. So this is the general antiderivative, or the general solution. And then because they gave me a point, I've got to plug in t and p. So p is 100, c e to the 0 minus 4. So again, e to the 0 is just 1. So I have 100 equals c minus 4. Add my 4. 104 is our c value. So my final answer should be p equals 104 e to the t minus 4. Now, example 5 is actually the one exception to the rule about don't add or subtract to move the variables around. If you have something on the same side as the dr dt or the dy dx or whatever it is, in this situation it's the dr dy, that you need to first add or subtract to the opposite side. So you really want all of these equations to start with the dy dx or the d whatever by itself. So the first thing I want to do is subtract that r over. So I always want the differential equation part to be by itself. And now I'm going to treat this just like I did in example 4. Think about this as being all one term and multiply by 1 over 1 minus r. So on this side they cancel out and I'm just left with a 1. So over here I can now multiply both sides by dy to cancel out the dy in the denominator. So I have 1 over 1 minus r times dr equals 1 dy. And I want to take the antiderivative of both sides. So again, 1 over a variable is ln. So this is going to be ln of 1 minus r. But you have to think about the fact that this is a negative r. And so really you would be dividing by -1. So that makes this whole thing negative. Just like if you had 1 over 2r, you would have to divide by 2. On this side, 1, the antiderivative of 1 will be y, because we have a y here. So make sure you use matching variables and put your plus c. So now in this one, we're actually going to solve for r. I cannot just take the e of both sides yet, though, because of this negative. So the first thing I'm going to do is divide the negative to the other side. And again, I don't have to apply the negative to the c. C represents any number, so c may or may not be positive. We don't know, so it really doesn't matter. If you multiply negative c by -1, it becomes positive c. If you multiply positive c by -1, it becomes negative c. But negative c is still any number, so it's all taken care of. And now I can take the e of both sides. So I get 1 minus r equals e to the -y plus c. So I'm just going to bring that c down. I'm going to subtract 1 And then I'm going to multiply through by another negative. So I end up with r equals negative c e to the negative y plus 1. Because I had to multiply all the terms by negative 1. And then again, I'm going to use the given point, so this is 0 and this is r, to solve for c. So, and again, e to the 0 is 1, so I get 0.1 equals negative c plus 1, so I'm going to subtract 1. 0.1 minus 1 is negative 0.9, and so c is positive 0.9. So our final answer is r equals negative 0.9 e to the negative y plus 1. Now, example 6 is going to be a little different. We are still going to solve it first, but then we're actually going to talk about domain and range, or just domain, and we're going to use the slope field to think about domain. So let's start by solving. So this is actually a pretty simple one. dy dx equals y. The only thing we need to do to separate this is move the y to the other side. So we got to multiply by 1 over y. So we get 1 over y dy dx equals just 1. And then we have to multiply by both sides by dx. And then we'll integrate. 1 over y becomes ln y. 1 becomes x plus c. Take the e of both sides. So we get y equals c e to the x. And we've already got the slope field over here for this differential equation. If you put this in the calculator, the slope field would come back to look like this. So the question is, what is the domain of the solution curve through the point 0, 1? So if you come here, 0, 1, let's say it's right here. If I draw this curve in, it's going to look something like this. It's just going to look like a normal e to the x graph. So what is the domain of e to the x? Well, it's all real numbers. Same thing if I draw it through 0, negative 1. 0, negative 1, the curve's now going to look like this, but e to the negative x still has a domain of all real numbers. Okay, last example, example 7. So we have dy over dx equals x over y. So again, we want to separate this. So the first thing let's do is get that y out of the denominator. So we're going to multiply both sides by y. So we get y dy dx equals x, and then multiply both sides by dx. So we get y dy equals x dx. And this is very similar to the one we did in number 1, we just don't have the negative sign. So take the integral of both sides. We get y squared over 2 equals x squared over 2 plus c. We can multiply through by a 2. And we can write this one of two ways. We can write this as y equals plus or minus square root x squared plus c. Or you can think about this as actually being a hyperbola. And a lot of times, when you have a hyperbola, you get x and y on the same side. And so you would have y squared minus x squared equals c. You may see it written both ways. If we go back to example 1 for a minute, when we did this one, another way we could have written this is actually a circle. So we could have just written x squared plus y squared equals c, if you move the x squared to the opposite side. So sometimes you may see the equation in this form rather than solving for y, and both are really acceptable in these cases. Okay, back to example 7. So we don't have a point to solve for c, that's okay, but what we can do is look at domains. So let's look through negative 2, 0. So negative 2, 0, let's say that's a point right here. I mean, we can't really tell from the scaling. We don't know what these little hash marks represent. But think about the point negative 2, 0. So I'm plugging that in here. If I'm going to solve for c, using that point, I get 0 equals plus or minus square root of negative 2 squared plus c. So 0 equals plus or minus square root 4 plus c. So I would square both sides to get c by itself. So c must equal negative 4. So I get y equals plus or minus x squared minus 4. Or again, you could write it as the hyperbola y squared minus x squared equals negative 4. Now, if you remember standard form of a hyperbola, you've got to get this to equal 1. So you have to divide by negative 4. So this really becomes negative y squared over 4 plus x squared over 4 equals 1. So you would like to say that this is a horizontal hyperbola that would go through this point, so it would look something like this. And so you'd like to say that the domain of that is x is less than or equal to negative 2. However, we need to go back and look at the original differential equation. dy over dx equals x over y. What is the slope at this point? If I tried to plug in negative 2 over 0, the slope is undefined. So the domain here is actually undefined. Now is this going to change for a point of negative 2, 0? Or I'm sorry, of 2, 0? So same idea. You'd have y equals plus or minus radical x squared plus c, and that point would be about here. 0 equals plus or minus. You still get 4 plus c, so you're still ending up with the same equation, y equals plus or minus x squared minus 4, which is still the same hyperbola, negative y squared over 4 plus x squared over 4 equals 1. We just now have the positive side of the hyperbola. But again, because it's the point 2, 0, if we try to plug that point into the differential equation, the slope is undefined there. Now for the last one, 0, negative 3, we flipped it. We can plug 0, negative 3 into x over y, and we just get back 0, and that's fine. So 0, negative 3, back to the slope field, is down here. So it's going to look something like this if you follow the shape of the graph. Or if you think about solving for c here, so I get negative 3 equals negative 3 squared equals c, because I got to square both sides. So 9 equals c. So I get y equals plus or minus radical x squared plus 9. Or if you write this as a hyperbola, and then you divide it by 9 to make it equal to 1, this is a nice vertical hyperbola, because the y is positive. And so the domain of this is actually going to be all real numbers.